Hello and welcome back to Calculus 1 on this glorious Saturday morning. Anyone with me? 3, 4 people with me. 5. We are going to talk about fundamental theorem of calculus. All of these derivatives and limits and integrals are called mathematical operators. Mathematical operators change functions. So derivatives and integrals would change functions. When you take derivative of x squared, which is a quadratic function, you get back 2x, which is linear function. Operations like addition and subtraction are operations that change numbers. So 3 plus 5 is 8. 3 minus 5 is negative 2. So operations would change numbers and operators would change functions. You learned that operations are paired as opposites. Addition, subtraction, multiplication, division, and then you have, let's say, exponents and roots, or exponents and logs. They're opposites, and they're opposites as operations. Now, in fundamental theorem of calculus, we learn that differentiation and integration are opposites of each other, and for the first time, you're looking at operators. Fundamental theorem of calculus has 2 parts to it. Part 1 of FTC, fundamental theorem of calculus, is what you already know. The integral a to b of f of x dx is any antiderivative f of x computed from a to b, which is f of b minus f of a, which is the way to compute definite integrals. Part 2 of fundamental theorem of calculus is the derivative of the integral of f of t dt is going to be f of x. And that's the one, part 2, that tells us that derivatives and integrals are opposites of each other, because this f of t is a lowercase f of t and f of x. That's the same value. So if same function. So if f of t is, let's say, sine t, then f of x is sine x. Let's test that. So we copy the derivative part, and then I'm asking you, what is the integral of sine t? What's the integral of sine t? Negative cosine t. And we have to compute that from 0 to x. Well, you're just plugging in the values that you have. So we still have this derivative in terms of x floating around. Negative cosine x minus negative cosine of 0. Compute this. Well, you can't compute the first one. It's just negative cosine x. The second one is 1. So we have plus 1. And now you take the derivative of it. The derivative of cosine is negative sine and the negative. Sine x. No matter what function you plug in here as a function of t, you will get the identical answer in the back as x. It seems like we just swapped the variables, but we are using t over there because you really don't want to use x because you have to plug x in. So you call this a dummy variable. You can put any letter, it doesn't really matter. We use t usually like t per time or parameter t, but it doesn't really matter. Whatever type of a function you have here in terms of t, you will get on the other end as a function of x. All I did is I integrated and then I went back with the derivative to the same thing. It did not change a bit. So that is what we have for fundamental theorem of calculus. And now we discuss this idea of definite integral versus the definite integral used as area calculations. So earlier, we solved the integral 0 to 2 pi for cosine x dx, and we got 0 because of the FTC1. Right? So FTC1, fundamental theorem of calculus, just computes the value for the integral. Its application is that it can be used to compute the area under the curve. But the answer is only valid if the function is entirely above x-axis. And that's the piece that it's missing here. So let's do the area. Well, I actually have to graph this in order for it to make sense. I will graph cosine from 0 to 2 pi. I'll put in these important values which you all know. And I will realize that I have two positive areas and a negative area. As a net area, what happens here is that these two positive areas are exactly the same size as the negative one. When they all add together, they cancel out and you get 0. This graph is perfectly symmetric, so they add to 0. But in some cases, you might have a graph that doesn't do that. You might have a graph that goes like this. And then you want to compute the area, let's say, from here to there. Well, clearly, this area here is not the same as this area there. So you're still going to get some kind of positive number, but that positive number is going to be the difference between these two. Fair? What you must do is you must be able to find the zeros of whatever function you have and apply absolute value on all negative areas. So any integral, and this is how the previous theorem, the one in purple, helps us. You are going to take this cosine function. 0 to pi over 2 is a positive piece above x-axis, no need for absolute value. Move along to the next piece between pi over 2 and 3 pi over 2. It's a separate integral computed from pi over 2 to 3 pi over 2, and you will apply absolute values because for that one you're going to get a negative number. Absolute value will make it positive. So technically what absolute value do is they bump that middle negative piece up. And then you will have 3 positive areas and they all add up and you will not have a 0. The same thing would happen for any other graph that you might have when it bumps up with the absolute value. Absolute value will bump that area up and you will have all positive areas to add. So the knowledge of the graph is important in this case because you have to know when the graph dips below x-axis. And for that interval, you have to use absolute value on the integral, which will bump it up. So now, looking at this picture, I have to write 3 integrals down. And I'm using the purple theorem from the property from the last lecture. So the area, is equal to integral 0 to pi over 2 cosine x dx plus the absolute value of the integral pi over 2 to 3 pi over 2 cosine x dx plus another integral 3 pi over 2 to 2 pi cosine x dx, and I don't need absolute value for that one because it was positive. So whatever pieces were positive, you go for it. So now, compute each one independently. You actually have 3 problems to work with. The first one is sine x computed from 0 to pi over 2 plus the absolute value of sine x computed from pi over 2 to 3 pi over 2, and then plus sine x computed from 3 pi over 2 to 2 pi. These are actually 6 calculations. So we have sine of pi over 2 minus sine of 0 plus absolute value sine 3 pi over 2 minus sine pi over 2, and then absolute value there, and then plus sine of 2 pi minus sine of 3 pi over 2. We compute all of those. What do I get? Sine of pi over 2 is 1, minus sine of 0 is 0, plus absolute value sine of 3 pi over 2 is negative 1, minus sine of pi over 2 is 1, plus sine of 2 pi is 0, and sine of 3 pi over 2 is negative 1, so negative minus 1. 1 plus absolute value of negative 2 plus 1 is 2 plus 2 is 4. The first time I saw this result in Calculus 1, I was amazed, because you are used to trig functions, right, having all the pi's and things going around, and the area under the curve from 0 to 2 pi is around 4. It's a whole number, no pi, which was amazing to me. So there you go. Any piece of a function that dips below x-axis has to be separated from the rest. And for that integral, you have to put absolute values, because eventually that integral will work out to be a negative number. An absolute value will make it a positive number, and then you will actually add all of the area. So how much do you get to color? How much do you get to color? You get to color, to shade in all of the stuff that is area. So let me give you a problem to work on for this. How about trying to think, x cubed would be a great one, because x cubed usually does that. Is this x minus 1 cubed? No, it's not. Um, x cubed minus x? Yes. Okay. X cubed minus x from -1 to +1. Actually, let's go to 2. From -1 to 2. So figure out the graph. You can use a graphic calculator. Right back. Give me 37 seconds. Silence means that you're not done yet. Or you're doing something completely different. No. Like lab 6. Oh, there's no lab 6? Do you want lab 6? So the graph looks like this. And it goes through -1 and +1. But I want to end at 2, creating 2 positive areas and 1 negative area. I'll do the negative area in red. You have to know where these breakpoints are, which are your A and B, and then any zeros that the graph will create. So now I will have the integral from -1 to 0 of x cubed minus x dx plus the red one, absolute value of the integral 0 to 1 of x cubed minus x dx plus the last one, integral 1 to 2 of x cubed minus x dx. The cool part here is that all of the antiderivatives are the same, so just computing the limits is going to change. So we have x to the 4th over 4 minus x squared over 2 from -1 to 0 plus the absolute value, the same thing, x to the 4th over 4 minus x squared over 2 from 0 to 1 plus x to the 4 over 4 minus 2x computed from 1 to 2. Just need to be careful. When you plug in 0, everything dies. Plug in -1, these are even exponents, so we have 1/4 minus 1/2 plus, again, 0 with polynomials, that all dies. I have 1/4 minus 1/2 in absolute values, plus 2 to the 4th is 16 over 4, minus 4, minus 1/4, and plus 2. I'm skipping a step of parentheses and all that because I can. 1/4 minus 1/2 is -1/4. Oh, that's a, yeah, this is a negative and this is a positive. It's a positive quarter. I gotta get the tick mark for that. But then I did the previous one right, so it's still 2-2. There we go. Was that a mean comment? Was that a mean comment? What did she say?
No, I was just saying,
It was gonna be 10 points off for you if you don't tell me.
I was just saying every time you get it wrong, it means that should be an extra credit point. Yeah, that's okay. I didn't hear that. Or it could be like the net. You know,
One quarter minus 1/2 is -1/4 in absolute values. 16 divided by 4 is 4, minus 4 is 0. 2 minus 1/4 is 1 3/4, which is 7/4. Altogether, 8/4 divided by 4 is 2, plus 1/4. So hopefully all of this is 9/4. If I did all of the calculations correctly. And if I haven't, it will not be another tick mark because it's per problem. No, it's good. 16 over 4 is 4, minus 4 is 0.
No, but you didn't integrate the -2x.
was supposed to say x squared over 2. Ah. So this is a 2 and a half, right? I need a shoulder, if anyone has. So 4 minus 2 is 2 plus a quarter. And I have 3/4 altogether. Like 11 over 4. It's my final offering. Great. 5.3 is done. Fundamental theorem of calculus, let me recap, has 2 parts. Part 1 is the way to compute definite integral. And depending on the value, depending on the shape of the function, it might or might not give us area under the curve. We are looking for the function to be entirely above x-axis to give us area under the curve. If it dips below, we will take that part on the side and make sure we apply absolute value on it to make it positive. The second part of fundamental theorem of calculus gives us the connection between the two operators, the derivatives and integrals, in a way that we show that they're opposites of each other. Every time you differentiate an integral, you go back to the original state, the original function. So technically, if you invert the sweater and it's upside down, right, outside, whatever, then you invert it again and you have the right side up. That's how it is. One more very short section, I believe consists of 3 formulas, and we're done for the day. So I will restart the stream